Hi guys, today we're going to finish up chapter 3, so let's get into it. First, starting with chapter 3.4 on finding and using slope of lines. So you probably all know how to do slopes and just finding slopes of an equation from pre-algebra. So I think this is a pretty simple review. But as you guys know, slope is the non-vertical line, which is a line of ratio of the vertical rise to the horizontal change. So rise over run between 2 points on the line, or for, as we know, a quadratic, not quadratic, sorry, linear equation like this. So there's different ways you can interpret slope, which is a negative slope, which is when it's like -2 or just a negative sign. Positive is when there's a positive sign. Zero slope is when the slope is something like this, and it's undefined if the slope is something like this. So that's basically the basic for slopes, and I think you can probably find the slope by yourselves. Let's look at two postulates related to finding the slope in general. So looking at the slopes of parallel lines, in a coordinate plane, two vertical lines are parallel if and only if they have the same slope. So something like y equals 2x or y equals 2x plus 4 would be parallel lines because they have the same slope, even if their y-intercept is different. And the slope of perpendicular lines is something like y equals 2x and when y equals -1/2x, which would show the relationship of a perpendicular line. And we can just tell that by looking at the slopes. So I think, honestly, this chapter is really straightforward, especially because it's a review of algebra, pre-algebra specifically. But if you just look at maybe, let's graph a line with a given description. So through 0, 2 and parallel to the line through negative these points. So because we already know the y-intercept is 2 because they gave us the point. And when we find slope, we do 1 minus 4, -5 minus 2, which is -3, -3, 1. So we do slope is 1. So we can write y is equal to x plus 2. And we can easily just graph that. I think here we would just need the first quadrant. So something like this. When it's 0, it's 2, 1, 3. So there would be a line, something like this. Would be number 27. And I think you got it, most of it. So let's look at writing and graphing the equation of lines. So as you know, even in linear equations, there's many forms. Like for example, the slope-intercept form, which looks like this, where m is the slope and b is the y-intercept. So I think this is a pretty straightforward example. This is, pretty easy, but know that you can check your answers by graphing. Because if you think two lines are parallel and if you plot them and they're not parallel, it's probably not parallel. And you can tell that from graphing, right? Yep. So you can obviously write linear equations with just the points. So more problems here. And honestly, this is really another review of pre-algebra. So I'm not going to get too deep into it, but let's just look at number first 35. So write an equation of the line that passes through point P and is perpendicular to the line with the given equation. So first, we should probably isolate the y here, which is 3 over 5x minus 6, 5. So this is the equation here. And when you're trying to find a line perpendicular to that line, first we can know that the slope would be y is equal to -5/3x plus b. And to find b, we can substitute this point here. So 0 is equal to and because we multiply this backwards here, the answer is probably 24/5 as your value, which means that the perpendicular equation is not b, but 24/5, and that would be your answer. Yep. Quickly, if you want to graph, let's graph 44, for example. We know that the equation is also equal to this, and we can simply graph it like this. And 0 would be 2, so 2, 1 would be negative, actually. Oh, here we go. If you have 1, then that's -1. So if this is -1, So it'll be something like this would be the graph of number 44. And I think that's about it. So lastly, let's look at some proving. So prove theorems about perpendicular lines. So these are some really basic theorems about perpendicular lines. So if two lines intersect to form a linear pair, remember equals 180 degrees of congruent angles, then the lines are perpendicular. So if lines intersect, as we can see here, to form and a linear pair of congruent angles, which means 1 and 2 is the same, then the lines are perpendicular. Obviously, for 180 to have congruent angles, it has to be 90, 90, which is perpendicular, because 90 degrees is a right angle, which is basically the basis of a perpendicular line. Here, the second term says if two lines are perpendicular, then they intersect to form four right angles. This is also pretty straightforward, because from the previous theorem, we know that here is 90 and 90, which also means that the 90 below here would also be the angles here would also be 90. So this is also pretty straightforward. And lastly, let's look at this theorem, 3.10. So if two sides of two adjacent acute angles are perpendicular, then the angles are complementary. Because recall that perpendicular is equal to 90 degrees, if you have two angles that are complementary, which means has a sum of 90, then that means that totally the sum would be perpendicular or a right angle. And now we have two more theorems. Hopefully this is the last. But first we have the perpendicular transversal theorem. So if a transversal is perpendicular to one of the parallel or of two parallel lines, then it is perpendicular to the others. And this makes sense, because if the line is here and they're parallel, that means they have to be right angles. And now looking at lines perpendicular to a transversal theorem. So in a plane, if two lines are perpendicular to the same line, then they're parallel to each other. So here we can tell M and N are parallel. This was the last. So let's look at number 10. So explain how we would show that M is parallel to N. So looking at the angles here, we know here is a 90-degree angle. And recall that let's just go back for the sake of it. Here. From the perpendicular transversal theorem, we know that if one line, if there's a transversal and one line is perpendicular, then the other is also perpendicular. So we can use that to conclude that M is parallel to a line in this case. And I just want to take a look at one proof here. Let's just look at proving theorem 3.8 before moving on. So we're given 1 and 2 are a linear pair, and that 1 is equal to angle 2, and we have to prove that they're perpendicular without using the theorem, obviously. So here 1 and 2 are supplementary. I think this is pretty much the definition of, I think you could also, here, like there's many things. You could use the definition of a supplementary angle, or I think you could also use the linear pair theorem, because pair postulate, because that also states basically the same idea. And definition of supplementary angles is used to show that. Oh wait, what is given? Measure angle 1 and measure angle 2 is equal to 180 degrees. And this given, this is just the definition of congruence, because, or you could even say actually equality in this case. Substitution property, combining like terms because they're the same value. And this is because, honestly, division property of equality would be correct here, because you're dividing the two over there. Equality and the definition of a right angle would be just that. Because we know measuring the 1 is 90 degrees. You can also, and this would be the depth of perpendicular angles. Yeah, sorry about the handwriting, but anyways, That's it for chapter 3. And now we're done. So great job everyone so far. And next we'll go on to chapter 4 about congruent triangles, which is probably, in my opinion, the highlight of geometry because it's really where the best proofs come out. So thank you guys. Bye.